It's on. Good afternoon, everyone. I welcome you all to this webinar titled Staged Malware Architecture in Android. So, let me start with a question that gets to the heart of the modern Android malware. Why would a skilled attacker ever put their malicious code directly into an app and upload it to Google Play? They won't, right? So that would be like a bank robber walking into the police station directly with a mask on. It's absurd. So, how do they get past Google's defenses? The answer is a class of malware called droppers. So, how these droppers work and all, we would go into a little bit of detail. And today we are going to dissect them from the inside out, not as a general overview, but as a technical deep dive. First, let's define what we mean by a dropper. In classical malware terminology, a dropper is a program that delivers, installs, or executes another piece of code. The key is that the initial file, the one that lands on your device in the first place, is not the final malicious payload. It is just a staging mechanism. Historically, malware was a monolithic. Think of the old Windows viruses, a single executable file which contained all the harmful logic. That was in the past days, in the olden days, in the earlier days of this malware. That model is dead. Why? Because the detection systems they have improved. In a static analysis, which is looking at the code without running it, became very good at spotting known signatures, suspicious API calls, and unusual permission combinations. So because this static analysis has improved, the attackers they also have adapted. They moved from monolithic to multi-stage execution. The first stage is a carrier. It looks harmless and it behaves harmlessly also initially. Only later, under specific conditions, does it bring the real attack. This is the core concept we are exploring today. A dropper is not a malicious program in a traditional sense. It is the beginning of the malicious process. So it is like the dropper system. It is like it is a continuous process. It is a continued process. It is not just a one-step mechanism. And understanding that process requires us to think not about code, but about time, the state, and the triggers. Let me give a recent example. In 2024, researchers they discovered a dropper family named Antidote. It appeared on Google Play, disguised as a simple PDF reader, the kind of app millions of people download without thinking, because it looks like just like a PDF reader. It had over 50,000 installs already before it was detected and pulled by the Play Store. The initial APK passed all of Google's static checks. It requested very minimal permissions also, not very suspicious permissions. It requested very minimal permissions, so it was not subject to any suspicion. People were simply giving. It requested like storage and maybe internet, and there were no red flags. But 2 weeks after installation, on a specific trigger, which is like the user opening the app for the third time, it downloaded a second stage payload from a remote server. That payload was a full banking Trojan, capable of overlaying fake login screens on top of 20 different Indian banking apps. So it has a trigger setup like the user has to open the app 3 times, and then there will be several kinds of triggers, and also they will be used in a combination also. We will see them in further slides. So what happened was, after it was triggered, it has downloaded another malware, another piece of code, and that could work on 20 different banking apps, Indian banks. So, and then it stole credentials, it intercepted OTPs, and performed a device takeover. This is not just theoretical. This is happening right now. This kind of attacks are happening right now. And the reason it works is because the initial app was never malicious at the time of inspection. The attack was delayed. So, as we go through this talk, I want you to shift your mental model. Don't think, is this app bad? Think, under what conditions could this app become bad? That is the proper problem. So now let's formalize why droppers exist from an attacker's perspective. It comes down to constraints, specifically the constraints imposed by the Google Play Store. It has the and the Google Play Store's security architecture. When a developer uploads an APK to the Play Store, Google runs a series of automated and sometimes manual checks also. The most important for our discussion is the static analysis. Static analysis means examining the code without executing it, without running the code, just study and try to find if there are any signatures that map with already historical signatures that are considered, that are categorized as the malwares. So the system looks for known malware signatures, suspicious API calls like a dex class loader or a runtime.execute file, unusual permission combinations. Example like a flashlight app requesting read context. So and patterns of obfuscation also. Static analysis has a fundamental limitation. It can only see what is present in the APK, but it cannot predict runtime behavior. It is very difficult to predict a runtime behavior. So attackers, they exploit this by splitting the app's behavior into two categories. First is a static behavior that is visible during inspection, and the runtime behavior that only manifests after installation. Let me put this into simple terms. The attacker designs the APK so that when Google looks at it, Google's security architecture in the Play Store, when it looks at it, they see a perfectly harmless app. Maybe it could be a calculator or some wallpaper gallery or something. The code is clean. The permissions also minimal. The strings are not obviously malicious. So because of all this, it passes all the tests. But hidden within that app, often in encrypted form or as a seemingly harmless assets, or more commonly not present at all, is the ability to fetch and execute the code later. This is the essence of a dropper. We may ask, so why not just embed the malware in the APK and use obfuscation to hide it? The reason is because obfuscation is not perfect. Google has a de-obfuscation tools also, and even if the code is obfuscated, the presence of certain patterns like dynamic class loading with the external sources can raise flags. So for the attacker, the safer strategy is to not include malicious code at all. So the attacker will be in a safe side. He will see that he doesn't want his code to be flagged. So he would take all necessary precautions to see that his code is not flagged by any of the security features that were laid in the Google Play Store. This is a classic. evasion technique. So in the this is not in the initial version. So in the initial version, he will see that the code looks as harmless as possible. The attacker shifts the malicious intent from static space, where detection is so strong, to runtime space, where detection is weaker. Because during the runtime, detecting issues is very difficult. So he would switch it. He would switch his attack to the runtime behavior, where the detection is weaker, especially over short time windows. We can model this formally as a trade-off. So droppers are an architectural response to the imbalance between static and dynamic detection. Because there is a lot of imbalance between the static and dynamic detection. The attackers, the hackers, they have moved their attack from static to dynamic state, dynamic detection to the runtime behavior. In the earlier stages of the malware, all the focus, all the attack was during the static behavior of the app itself. But later they have, because the app detection, it has changed, it has adapted, it has improved a lot. They have moved to runtime attack. They exploit the fact that when what an app does at runtime can differ dramatically from what is visible statically. And as we will see, Android's own features, because this Android system is new, it is not like the old operating systems that runs out desktops and servers and all. This is new, and it has some features that are enabled. Uh, these attackers, these hackers, they exploit this Android features, and then they run their malicious code. We will see them in detail. Now let's get precise about definitions. In security literature, terms like a dropper, downloader, loader, and a Trojan are often used interchangeably. But from a technical perspective, there are clear distinctions. A Trojan, short for a Trojan horse, is a program that appears legitimate but contains malicious functionality within itself. The payload is embedded. When you install a Trojan, the bad code is already there, just waiting to be activated. The original Juice banking Trojan was a Trojan in this sense. It was a single binary. A dropper, in contrast, does not necessarily contain the payload in usable form. Its primary purpose is to deliver the payload, either by extracting it from embedded encrypted data or by downloading it from the remote server. So he could even keep the malicious code in a very encrypted form. We will see the details in further slides. The defining characteristic is that the payload is separated from the initial character. That is what separates the dropper from other family, other things in the same family. So, and a downloader is a subtype of a dropper that specifically fetches a payload over a network. So there is a distinction between all of these, like a Trojan dropper, a downloader, and a loader. And this is the primary difference. A loader is a component that focuses on executing the payload, loading it into memory, and invoking its entry points. In a real world malware, these roles are often combined. A single application may act as a dropper, that is, it carries an encrypted payload, also as a downloader, that is, it fetches additional modules, and also as a loader, it executes them. So they could, in a real world, what happens is that they would make a combination of all these types. So while the distinctions are useful for analysis, in practice, we talk about dropper families that include all these capabilities. So for discussion sake, though we will separate them, we would include all of these and we talk as a single thing called dropper family. We include all of them and then we'll address this concept. The critical concept in all of this is the staging. So that is why we are talking about the staging architecture of the malware, Android malware. Staging means that the full malicious functionality is not immediately present or visible. It is introduced in the later phase, often after the app has been installed and run for some time. We may ask, why is staging so powerful? It is powerful because it defeats the assumption that all executable code is contained within the APK. Mostly, security tools are designed to inspect the APK. When we give the APK to the Play Store, Google Play Store, all the tools they mostly work on this APK. If the real code comes later, after the inspection window has closed, these tools are blind. So it would easily pass all the tests that were run by the tools that run on the during the API when the APK is first installed. Because no malicious code would be present, so it would pass all the steps and even the permissions that it requires would be very minimal, and so they would not raise any red flags. Let me give you an example. An APK file is essentially a zip archive. So people who are well acquainted with the Android development, all they know this. But for the people who are not aware, um, an APK file is essentially simply a zip archive. Inside, you have classes.dex file. Dex means Dalvik executable bytecode that Android runs. And there is also Android manifest file. It is an XML file and that declares the permissions and all the components that are used in the APK file. And there are resources files also, and all of them are put together and made into an APK file. A dropper might have a classes.dex that is only a few kilobytes. It contains code to set up a dex class loader, a network client, and a trigger mechanism. That's it. The real malware may be 2 MB of bytecode, is either stored encrypted in the assets folder or downloaded later. At the static analysis time, that 2 MB payload is either invisible. So during the initial static analysis done by the Google Play Store security architecture, it is either made invisible by making it as an encrypted one or not present at all. Also, that if the hacker thinks that he would not give even the most minimal suspicion, then he could make it completely absent also. It would not be present in the APK file itself. So the scanner sees a small, harmless looking app. What I'm saying is this is not just a theoretical construct. This architecture is already being used by dozens of active malware families, and it works. It is really working. The hackers are able to bypass all these security features of the Google Play Store using this simple logic, a simple technique. So let me cite some real world examples. I will focus on consumer grade droppers that have widely been documented. So there are many that are not documented, but we would go, I would cite a few of them that were documented. First one is the Joker malware family. This is a textbook example. Joker first appeared in 2017 and has resurfaced repeatedly under different names and disguises. The typical Joker dropper is a utility app like a keyboard, a wallpaper changer, a messaging sticker app, or a PDF reader, etc. It gets uploaded to Google Play Store. It passes all static checks and gets installed by hundreds and thousands of users. After installation, the dropper does nothing immediately. Immediately, it doesn't do anything. It will behave just like a normal app and what it was intended to do. It waits. Then, depending on the variant, it has several variants, right? Depending on the variant, it either downloads a second stage APK or dynamically loads the another dex file. That payload subscribes the user to premium SMS services without their consent or knowledge. It would subscribe to premium SMS. The user only discovers this when they get a huge phone bill. What makes Joker particularly interesting is its flexibility. Between 2019 and 2022, Google removed over 2,000 Joker related apps from the Play Store, but still new ones kept on coming. Why is this possible? Because the dropper pattern is easy to vary, easy to change. All the hacker has to do is, okay, the Google Play Store has detected one of these Joker malware. So, and it has removed, Google has removed. Then all the hacker has to do is very simple thing. He has to change the icon, change the app name, change the obfuscation, and the static signatures no longer match with what Google has already detected and found and removed. Then he would again upload another one. So the core dropper logic remains the same, but the outer shell is constantly mutated. All the hacker has to do is just change the outer shell of the app APK, and the internal logic it stays the same. The second example is the T-bot or ANATSA banking Trojan family. So these are more sophisticated. They target banking credentials only. In these cases, the dropper is often a QR code scanner, a document scanner, or a phone cleaner app. Again, it passes all the Google Play Store security checks. But after installation, the dropper waits for a trigger, sometimes a specific day or a specific time of day. Sometimes a user action like scanning a QR code. Once triggered, it downloads the full banking Trojan. That Trojan then asks for accessibility permission under a false pretext like enable this to improve battery life or enable this to clean junk files. If the user grants it, and many people do, when they see this option, people would generally give permission. And when they give the permission, most people would usually give without a second thought. Then the Trojan can read the screen because it is an accessibility permission. It can read the screen. It can simulate taps and intercept notifications. It can wait for the user to open a banking app, then overlay a fake login screen that steals the credentials. It can also forward OTP messages because the accessibility permission is enables the app to do all these things. And according to a report by Cliffy, T-bot variants have targeted over 400 banking and financial apps across Europe and Asia. In India alone, over 20 banks have been impersonated. The dropper stage is what enabled these attacks to happen at such a large scale. And the third one is the Sharkbot malware. This is another banking Trojan that used droppers disguised as antivirus apps and file managers. Sharkbot introduced an advanced feature, that is automatic transfer system, also known as ATS. Once it gained access, it could automatically navigate the victim's banking app, and then it could initiate transfers and complete them using stolen OTPs, all without any user interaction beyond the initial permission grant. All this Sharkbot needs is the one permission. by the user to that is the accessibility permission. Once it gains that permission, it doesn't need any user interaction. It could go and find uh, that banking app, and then it can initiate the transfer, and it could use the OTP. Everything happens in the background. The pattern across all these examples is consistent. The initial artifact, that is, the app on the Play Store, is not the full threat. It is only the first stage. The real attack is staged, it is delayed, and often hidden behind legitimate looking triggers. To understand how droppers work at the system level, we need to examine specific properties of the Android platform. An Android application is packaged as an APK file. If you unzip an APK file, just like any other zip file, we can just unzip it. You will find several components like this. First one is the Android manifest.xml. This declares the app's permissions, activities that are used in the in the app, and then the services it uses, and the broadcast receivers and content providers. It's essentially the app's identity card. This Android manifest is like the identity card. It will give all the information about the APK file, all the activities that is going to use, and all the permissions. Everything is given in the Android manifest file. And secondly, the classes.dex. This is the compiled bytecode for an app written in Dalvik bytecode format. It's what the Android runtime ART, when ART executes, it will execute this dex file, just like Windows executes the exe file. The Android runtime ART, it will execute this uh, ART. ART executes this dex file, classes.dex file. Thirdly, resources.asrc and a resources folder. So these contain images, layouts, strings, and other resources. Fourthly, lib folder. This contains native code libraries .so files for different CPU architectures. And finally, the assets folder. This is the catch-all folder for the arbitrary files. The app can read them at runtime. So whatever files we keep in this assets folder, the app can simply read. It doesn't need any permission, any extra permissions. It can simply read. That is the native behavior of this thing. So at runtime, Android uses the ART runtime to execute applications. Unlike older versions of Android that used ahead of time compilation exclusively, modern ART uses a hybrid approach. It compiles frequently used code ahead of time, but can also compile just in time. So for our discussion, the compilation details are less important than a specific feature, that is dynamic code loading. Dynamic code loading is enabled by two classes. They are Dex class loader and path class loader. Path class loader is used to load classes from the APK itself. It is the standard class loader for installed apps. Whereas a DEX class loader is more powerful. It can load classes from arbitrary DEX files stored anywhere on the file system. For example, a file downloaded from the internet and saved to the app's private data directory. From there, it can simply run. So DEX class loader is more powerful and more dangerous. So here is how a dropper uses this feature. The app first downloads a DEX file from a remote server. It saves it to a location like data, and then com.example.app, and then it saves as a payload.dex. This is the usual behavior of all the drops. Then it creates an instance of the DEX class loader, passing the path to that file. So to run it would create a new instance, and then using the reflection. we would cover all these concepts in further webinars. So using reflection, because the class names are not known at compile time, it loads a specific class from that text file and calls a method, usually something like a start or init. This is a legitimate feature. So it wouldn't find the ART Android runtime would not find anything suspicious in it, because this is normal behavior of any DEX class loader. It would download a file and then try to run it. This looks like a normal behavior, not any suspicious. So it's used for things like dynamic feature modules, plugin architectures, and in-app updates. For in-app, we'll be seeing, no, when we're running, we'll see like a new update is available for this app. So all this happens because of this Dexel class loader only. So the security features in the ARC and they don't flag it. They don't see anything unusual. They see it as a normal behavior. So it is not flagged. So time is up. So I will stop it here, and then we will continue in the next slide. Thank you very much for joining me and in this webinar, and allowing me, giving me opportunity to share a few of the things that I know from this Android list. Thank you very much.